So these limits are examples of some standard limits whose values you need to know.
Okay.
Uh, all of these limits are equal to 1. Okay, so do you know the proof of everything, these limits?
No, but you had told sine x by x before.
Yeah, sin x by x, we had drawn that diagram of a circle, right?
Yeah.
We had drawn this circle diagram, and we saw that if you take a point here and circle radius is 1, let's say, and this angle is, let's say, x, then drop a perpendicular like this, join this and extend it a little, and then drop a perpendicular from here to this, right?
Yeah.
So we saw that this triangle area is less than the area of the sector and is less than the area of this triangle, right?
Yeah.
However, if you bring the point P close to the x-axis, right, what
Yeah.
happens is all three areas become equal, right? All three areas start becoming very close and close.
To each other. Yeah.
If you take the area of this inside triangle, that area will be half into base into height, and base uh, half into base into height, right? Oh, actually, the area of the triangle is not this triangle. One second. It's the area of the triangle drawn like this triangle. Okay. So, and you have dropped a perpendicular like this. Okay. And the outside triangle is from here to here, right? So, I will label it 0, A, O, A, B, and this is C. So, triangle OAB. Okay. Triangle OAB, the radius of the circle is 1. So this distance is 1, this distance is 1, and this angle is x.
X.
So this perpendicular will be sine x, right?
Yeah.
Perpendicular will be sine x. So half into 1 into sine x is the area, right?
Yes.
And if you look at the outside triangle or triangle OCB, the perpendicular in that case will be tan x, right? This one.
Yeah.
This is tan x. So half into base is 1 into tan x.
And x.
And the sector area is the OAB sector, right? Will
Yeah.
be x by 2 pi into pi r square, right?
Yeah.
X by 2, r square is 1, so x by 2, right?
Yes.
So all the three areas are basically x sine x by 2, x by 2, and tan x by 2.
I do.
And in the limit that you bring the x angle close to 0, all three areas should become equal, right?
Yes.
Because when the angle becomes smaller, you can see that the difference, this difference and this difference
Reduces.
will become smaller and smaller, right?
Yeah.
So what we will have is, in the limit x tends to 0, sine x by 2 will tend to x by 2 will tend to tan x by 2.
I do.
All three will be same. So you will get sine x by x will tend to 1, and similarly tan x by x will tend to 1, right?
Yeah.
However, there is a slight difference in both the tendencies, that sin x by x is tending to 1 from less than 1, right?
Yes.
Sin x by x, this area is technically still less than this, right? This is less than this, and this
Yeah.
is like this, it is, right?
Yeah.
So sin x by x, when you do, that will be less than 1, and tan x by x will be greater than 1. So this limit is tending to 1, and this limit is also tending to 1. However, this is tending to 1 from 0.99 side, and this is tending to 1 from 1.01 side,
Yeah.
right? So these are standard limits that we need to know. Then we need to know these two also. So these two will derive now. After that, what we will do is, after the standard limits, we'll learn some limits by series expansion, series expansions. Then we'll look at uh, sandwich theorem, and some limits from there. And finally, we'll look at some exponential limits.
All right.
So let's look at the series expansion stuff. So series expansion will help us basically prove these things, prove the limits e power x minus 1 by x is equal to 1, and also help us prove log 1 plus x by x is equal to 1. Okay. So
Okay.
by the way, the standard limits are stuff that you need to know, so that many questions it will be in framed in such a way that you can convert it to a standard limit type. So for example, you might be given questions like this: limit sine x tends to 0, sine 2x by 3x, right? So then
Yeah.
what you can say is that in the standard limit you had something like this, right? Sine x by x, where x was tending to 0, right?
Yeah.
So the argument of the sine function should match the denominator. So I will try to match it here, and I will basically write it as 3x. I will write as 2x into 3 by 2, right?
Yeah.
So this becomes sine 2x by 2x, and on top becomes 2 by 3, right?
Yeah.
So now notice that if x tends to 0, this argument is matching this argument and both are tending to 0, right?
Yeah.
Which is the limit form, which becomes 1, right? So this part will become 1 and answer will be 2 by 3.
Right.
So that is how there will be several more manipulations that you can do. Also, you can also think of it in this way, which I don't recommend so much, but you can think of it as L'Hopital rule also. This is 0 by 0 form, right? So
Yeah.
you can differentiate the top cos x by 1, right? Limit x tends to 0.
Yeah.
And it stops here because the form has gone now. 0 by 0 is not 0 by 0 now, right?
Yeah.
And you put 0, it will become 1, right?
Yeah.
So by L'Hopital's rule, you can derive all of these very easily, right? But uh, that is a last resort. You should only use L'Hopital when nothing else is working, because many times what happens is they will frame questions in such a way that differentiating will be painful. Okay, so ideally think about other things also. So what we look at now is the series expansion stuff. So let's see. So there is something called Taylor's theorem. Okay, Taylor's theorem in calculus that you might learn later, but right now we'll need that to be able to prove this series. So Taylor's theorem says this: f of x will be equal to f of 0 plus f dash 0 x power 1 by 1 factorial plus f double dash 0 x square by 2 factorial plus f triple dash 0 x cube by 3 factorial plus so on, this pattern.
All right.
So notice the pattern here. First thing is f of 0, value of the function at 0. Then the second coefficient here is derivative of fx, and then put the value 0 in that.
Yeah.
And x power 1 by 1 factorial, that is the x coefficient, x powers. Similarly, second one is double derivative of f, and then put the value of 0 in that, and x square by 2 factorial, right?
Yeah.
So what is happening here is that you are approximating, this is an approximation of fx using an infinite series, approximating, basically approximating fx by a series expansion, right?
Yeah.
Instead of fx, you are able to write fx even like this, right? So by this infinite series, this keeps going on forever. Okay,
Okay.
so the point is that obviously this expansion is valid only under certain conditions. The conditions are continuity and differentiability should be ensured. Right now you don't know those things, but most of the time you don't have to worry about whether this is valid or not. Most of the times it will be valid for the functions that you will encounter. So
Uh,
what you will be able to say is fx can always be written like this. And let's do some examples so that we understand how to write it. So for example, if fx is sine x, right?
yeah.
Fx is sine x. So what is my f of 0? It is 0, right?
Yeah.
F dash x, first derivative is cos x, and f dash 0 is equal to 1.
Yeah.
Double derivative is minus sine x,
Next.
and
Yeah.
f double dash 0 is 0. Then
Yes.
triple derivative, triple derivative of x is minus cos x, and f triple dash 0 is
Demand.
minus 1, right?
Yeah.
And so on. So now what we will do is we'll just approximate sin x. So sin x becomes f of 0 is 0. We'll put the
Mm.
values. 0 plus f dash 0 is 1.
Is 1 by 1 factorial.
1 into x power 1 by 1 factorial. Second term is 0 because this part 0. 0. Third term, however, is minus 1 and it becomes x cubed by 3 factorial, right?
Yeah.
Fourth term will be 0 because see, derivative of this will become sine, right?
And yeah.
Fifth minus, it will become plus sine, right?
Yeah.
Derivative.
And
So,
we
so the next one, fifth one will become plus cos, right?
yeah.
So fifth one will not be 0, right?
Yeah. Fifth one will be the second one again.
Fifth one will be like this, right? So,
Yeah.
and so on, the series continues. Every odd term is present, every even term is not present, even powers, right?
Yeah.
So sin x series you have gotten as x minus x cube by 3 factorial plus x power 5 by 5 factorial minus x power 7 by 7 factorial, and there is alternating signs, right?
Yeah.
This is the series that is coming, right?
Yeah.
Now, once you're able to write the Taylor series for anything, it is going to be super easy to then find the limit, because now see, if sin x was this, sin x by x would have been what? 1 minus x square by an x4 and all, right?
Yeah.
And sin x by x, now put limit x tends to 0 here. It's super easy to put limits in this one, right?
Yeah. Everything becomes 0. And not.
Everything else becomes 0 except 1, right?
Yeah.
So you get limits x tends to 0, sin x by x is 1, right?
Yeah.
So this Taylor series formula you should write down, super important, because otherwise what happens is people expect 11th and 12th grade students to memorize lots of series. You cannot memorize them, okay? It is difficult to memorize them. So for example, in the coaching book, for example, in Allen book, they have not given the Taylor series expansion, but
And
they
they give
have
the cards.
asked you 10 different series to memorize.
Yeah. We did the same.
Yeah. So that is not possible, okay? So you cannot memorize everything. So you need to be able to get it yourself if you have forgotten, right?
Yeah.
So the series that they have asked in this Allen book to memorize at least are these: e power x, a power x, sin x, cos x, tan x, then log 1 plus x, then uh, 1 second, then there is cos x, tan x, log 1 plus x, tan inverse x, sin inverse x, tan inverse x, sin inverse x. Then they have also given cos sec inverse x for some reason, I don't know why, and 1 plus x power n, sec inverse x, and 10th one is binomial series, 1 plus x power n, right?
Yeah.
However, it is impossible to memorize so many series because they are very similar terms, no? So what I want you to do is use your Taylor theorem that you have written, right, to find e power x, log 1 plus x, and tan x, okay? For now, find these three, right? Because we'll use these to get, okay?
Yeah.
Use Taylor theorem, just apply them properly and you will get these three series. Once you can write these three series, we'll get three standard limits, okay?
Okay.
You copied the Taylor theorem down, no? That
Yeah. I copied it.
okay, so just apply it once and see what is coming. 3-4 minutes, I'll be back, okay?
All right.
Okay. Are you
Yeah,
getting this e power x1?
yeah, I got that.
So it will be 1 plus x power 1 by 1 factorial
X plus x power 2 by 2
and
factorial.
so on,
1.
right?
Yeah,
This type of series you will get because the derivative of e power x will be same as e power x,
yeah,
right?
yeah,
So every
yes,
derivative is same, so every coefficient will be 1, 1, 1, 1, right? So now you can
yeah,
see that e power x minus 1 will be simply x power 1 by 1 factorial plus x power 2 by 2 factorial and so on, right?
yeah.
And e power x minus 1 by x will be,
1 by 1 factorial plus x by 2 factorial and so on.
and now you can put the limit easily. This limit will become simply 1, right?
Yeah,
Okay. So similarly, let's do log and tan in the next page. So log 1 plus x is my fx. So f dash x is simply 1 by 1 plus x,
x,
right?
yeah,
So f dash 0
is
is
it?
equal to 1, right?
Yeah, yeah,
And f of 0 is 0, right?
yeah,
And f double dash of x will be minus 1 by 1 plus x whole square. So f double dash of 0 will be minus 1, and f triple dash of x will be the derivative of this. So that will become
my
2
plus 2
by
by
1
1
plus
plus
x
x
whole
whole
cube.
cube.
So therefore f triple dash 0 will be 2, right? 2
Yeah,
by 0, 2, right?
yeah,
So similarly, one more time we'll do. Fourth derivative of x will be 2 into minus 3. So minus 6 by
by 1 plus x whole to the
4.
power.
So fourth derivative of 0 will be minus 6, right?
Yeah,
So now if I write the function fx is equal to f of 0 is 0
yeah,
plus f dash 0. So 1 into x power 1 by 1 factorial plus f double dash 0. So minus 1 into x square by 2 factorial plus f triple dash 0 is 2 x cube by 3 factorial plus then minus 6 x4 by 4 factorial and so on, right?
yeah,
Now if you simplify it a little bit, this becomes x by 1 minus x square by 2 plus, see, 2 by 3 factorial is just 3, right?
yeah,
And this is we just 6 by
4,
24, so 4, right?
yeah,
And so on. So there's a nice pattern: x minus x square by 2 plus x cube by 3 minus x4 by 4 plus x5 by 5 minus x6 by 6. This is what will keep happening. Okay.
yeah,
That is your fx, which is log 1 plus x. Again, log 1 plus x by x, right, will become 1 minus x by 2 plus x square by 3 minus x3 by 4 and so on.
1,
And then you put limit x tends to 0, that becomes 1.
1,
So this is also one standard limit that you can know, which is going to be 1. And it is obvious if you know the series, right?
yeah,
So similarly, Tanic series is slightly annoying because derivatives become big, right? Tanic series, if you say f of 0 is equal to 0, f dash x is equal to secant square x, so f dash 0 is 1, and derivative of secant square x now. So that will be 2 sec x, and derivative of sec x is sec x tan x,
x, yeah,
right?
yeah,
This becomes 2 secant square x tan x, but because 0 you have to put, that will become 0 because of tan x, right?
yeah,
Triple derivative if you want to do, you have to do by product rule here. So differentiation this part once and this part then, right? So that will be, let's do the 2 secant square x term. So something will come from 2 secant square x term, right?
yes,
I don't care because tan x is multiplied, right?
yeah,
Because when you put 0, this will disappear, right?
yes,
The other part will I will care about because I will differentiate tan x, it will become secant square x, right?
yeah,
So when you put 0, it becomes just simply just 2, right?
yes,
So now let's write the series. So fx is equal to 0 plus this one. So 1 by 1 into x power 1 by 1 factorial. Second one is 0, right?
Yeah.
Third one is 2
2.
into x cube by
2
3
3
factorial,
factorial.
right?
Yeah.
And so after that, you'll have to do a little more to get other terms, but I don't care so much. It will be simply x plus x cube
You.
by 3, right?
Yeah.
Plus the next term turns out to be 2 by 15 x power 5, but you can do it by doing the derivatives, but it is annoying, so I'll not do it. So tan x by x will become what? 1 plus x square by 3 plus 2x power 4 by 15,
And so on.
so on, and limit will tend to 1 if you take x tends to 0. However, notice that every term here is positive, right?
Yeah.
So limit is actually, it is greater than 1 here, right?
Yes.
On the other hand, when you are doing sine x by x, you are getting 1 minus x square by 3 and some stuff like that, right?
Yes.
So that was slightly lesser than 1. Okay.
Yeah.
Okay, so the series expansions should be clear. And by the series expansions, we can find many limits. So we will see examples of that. But before that, let's go to the sandwich theorem part. Sandwich theorem part says sandwich theorem. So this says that suppose you have three functions fx, gx, and hx. And you have the condition that fx is always less than this and this is always less than this, right?
Yeah.
So the graphs will be in some way, it will be like this, right? This is suppose these are your fx and gx, right? This is hx, this is fx. So gx must be in the middle, right?
Yes.
Now, this could be any three functions which satisfy this condition. Then if by chance you have limit of x tends to some number a, fx is equal to limit of x tends to that same number hx, right?
Yeah.
Correct. So what is happening is as you come closer to a, the lowest function is tending to something and the topmost function is also tending to the same thing, right?
Yeah.
Then that means that the values of fx and hx are coming closer and closer, no?
Yeah.
So then the middle function is squeezed and it is going to be in the middle only, right?
Yes.
So then limit of x tends to a gx is also going to be the same thing,
Okay.
right?
Got it.
Because it will be squeezed, no? Because the top part will become some value and the bottom function is also tending to the same value, right?
Yeah.
So it seems like this is very contrived and it doesn't have too many applications, but many times you will find some questions where this can be applied. So for example, we will see, let's try to find out the limit of x tends to 0, x square into sine 1 by x. Okay.
Okay.
So right now, if you notice, the sine 1 by x is completely not defined properly, right? Because
Yes.
1 by x tends to infinity and the sine function will keep oscillating very rapidly, right?
Yeah.
However, what we can say is that sine 1 by x will always lie, sine 1 by x will always lie between -1 and 1, no matter what,
Yeah.
because it is a sine of something, right?
Yes.
So therefore, we can construct two other functions. We can say that x square into sine 1 by x will always be greater than minus x square, and this will always be less than x square, right?
Yeah.
Because this part is between -1 and 1, right?
Into one. Yeah. Got it.
And we can say that this limit is tending to 0, right? And this limit is tending to 0, right?
Yeah.
This also tends to 0, no?
Yes.
So this is going to be squeezed in the middle, right?
That will also have to tend to 0.
So it should also tend to 0, right?
Yeah.
Because the lower function and the upper function are both tending to the same value, 0, right?
Got it.
So this is an example of the sandwich theorem. We can also take another example, which is actually the same example. X into sine 1 by x, that also follows the same thing,
Yeah.
because it will be between minus x and x, right?
Yes.
One slightly more advanced example will be, let's do this one. Let limit n tends to infinity, gif of x plus gif of 2x plus gif of 3x plus so on, gif of nx by n square, nx by whole divided by n square. This is my thing. Now I have to find this limit. Now this is another example of the sandwich theorem. So where right now I have to analyze the numerator basically. So I know that the numerator GIF will always be less than equal to x, right?
Yes.
And it will be x minus 1 is less than equal to this, right?
Yeah.
This is always satisfied,
Yeah.
correct? No?
Yeah. Correct.
So GIF of 2x will be less than equal to 2x and 2x
Correct.
minus 1, right?
Yeah.
And so on till nx will be less than equal to nx and nx minus 1, like this, right?
Yeah.
So instead of on the numerator, if I construct functions like this and functions like this, add all of these, right?
Yeah.
So I can say that this sum will be less than equal to this sum and less than equal to this sum, right?
Yes.
Right. So if I add the two other functions, I will get x plus 2x plus so on till nx minus n on one side, less than equal to my function, less than equal to x plus 2x plus
And then,
nx, right?
yeah.
So this part will become x into n plus 1 by 2 minus n, less than equal to fx, less than equal to x into n plus 1 by 2, right?
Yeah.
Now let's divide by n square. Let's divide by n square. This by n square, right?
Yeah.
So we have to take limit n tends to infinity, right?
Yeah.
So on top here, let's do the division by n square here. So it will become x into n will cancel and it will be 1 plus 1 by n by 2, right? Minus 1 by n, right?
Yeah.
And less than equal to fx by n square, less than equal to x into 1 plus 1 by n by 2, right?
Yeah.
And when you take the limit now to infinity n, this term will disappear, this term will disappear, right?
Yeah. So it will be x by 2.
This is x by 2 and this is also x by 2. So the middle limit has to be
X
x
by
by
2.
2, right? So this is an example where you can make another sandwich theorem type of situation, right?
Yeah.
So okay, so sandwich theorem is this. Now let's look at, since we know some standard trigonometric limits, I will just list them down once more. We know that limit x tends to 0, sine x by x is equal to tan x by x, same limit x tends to 0, is also equal to limit x tends to 0, sine inverse x by x is
Yeah.
equal to limit x tends to 0, tan inverse x by x, and all of them are equal to 1. So we have not yet proved this and this, but again the proof is same. Proof is sine inverse x, write the expansion of it. Okay. So this will be slightly more annoying because of the root parts, right?
Yeah.
So derivative of sine inverse x, do you know how to do?
No, I haven't. I have the form. We had got it as a formula, but I don't know. I like.
Okay, so the way to do it is, this is my function and I want to do dy by dx, right?
Yeah.
I want to do dy by dx. So why not write x is equal to sine y, right?
Yes.
And differentiate this side, it becomes dx is equal to differentiate this side with respect to y, cos y dy, right?
Right. Yeah.
So dy by dx is equal to 1 by cos y, right?
Yes.
And since sine y was x, so 1 by cos y is root over 1 minus x square, right?
Yeah.
That is the differentiation. That
Okay.
is the differentiation of sine inverse x, right?
Yeah.
Because what we did is, because sine inverse x is y, we have x is equal to sine y, and then differentiate like this separately. This
Got it.
side differentiation is dx, this side is cos y dy, and then dy by dx I wanted, so I have isolated that, and cos y should be root over 1 minus sine square y, which is root over 1 minus x square, right?
Yeah.
So similarly, if I have to do differentiation of tan inverse x, right? So I will say x is equal to tan y,
Mhm.
and dx should be equal to secant square y dy. Therefore, dy by dx should be equal to 1 by secant square y, which is 1 by 1 plus tan square y, right?
Yeah.
Is 1 by 1 plus x square, correct?
Yeah.
So these are the derivatives. The problem will be that the other terms after that will be even more complicated, right? Because
Yeah.
you don't have to do just one derivative, you have to do a little more, right?
Yeah.
So let's try to do the sine inverse x once. Sine inverse x. So first I will do f of 0, right? F of 0 is 0 here, sine inverse 0, right?
Yeah.
Then I have to do f dash x. F dash x I know is root over 1 minus x square. Therefore, f dash 0 will be 1 by 1, right?
Yeah.
Now, double derivative of this, right? Double derivative of this is differentiation of this part. So this part is technically 1 minus x squared to the power minus half, right?
Right. Yeah.
So I will get minus half 1 minus x squared to the power minus 3 by 2 multiplied by minus 2x, right?
Yes.
This inside part derivative is this, right?
Yeah.
So now notice that because of this 2x being in the numerator, f double dash x is 0, right?
Yes.
Right? This one will be 0 because of
Yes.
this. Then triple derivative, this is the last derivative that we'll do. This will be because of, I will just simplify this expression a little. Minus half into minus 2 is plus 1, right?
Yeah.
So this is simply x into 1 minus x squared to the power minus 3 by 2, right?
Yeah.
So this derivative will be by product rule. First differentiate this. So you'll get 1 minus x squared to the power minus 3 by 2 plus
Yes.
x into derivative of this, right? So
Yes.
that will be minus 3 by 2 something powers here minus 5 by 2 into minus 2x, right?
Yeah.
However, we don't care about this term because you have to put x is 0, right?
Yeah.
So the term that matters is going to be this term, which will give you 1 only, right?
Yeah.
Because it is 1 by root 1 by 1 minus x squared to the power 3 by 2, right? And x tends to 0, right?
Yeah.
So we have three derivatives. So now I can write the function as f of 0 is 0, x f of f dash 0 is 1. So 1 into x power 1 by 1 factorial plus x square is 0. So and third one is 1. So third one is 1. So 1 into x cube by 3 factorial, right?
Yeah.
And so on, right?
Yes.
So I don't care much more. I just note that I can write it as x plus x cube by 3 factorial plus some stuff, right?
Yeah.
Right? So sine inverse x by x is definitely 1, limit x tends to 0. Divide by x, it will be 1 plus something, correct? In
Yeah.
a similar way, you can prove that tan inverse x by x is also 1. Okay,
Okay.
fine.
Yeah.
So now let's do some examples which use these trigonometric limits. So first one is limit of x tends to 0, x cube cot x tends to 0, x cube cot x by 1 minus cos x. 1 minus cos x. Second one is, you can try it. Uh, I will just write down a few questions. We'll discuss all of them.
All right.
Uh, Second one is limit of x tends to 0. 2 plus x sine 2 plus x. 2 plus x sine x minus 2 sine 2, 2 sine 2 by x. Third one is limit n tends to infinity sine of a by n by tan of b by n plus 1. Okay, these four examples. The first one, so this x cube cos x by 1 minus cos x, cot x. So because cot is annoying, I can convert to cos by sine, right? X
Yeah.
cube cos x by sine x 1 minus cos x, right?
Yeah.
Then uh, see, there are multiple ways to do it. One way to do it would be L'Hopital, right?
Yes.
Because notice that the denominator is tending to 0 and the numerator is also tending to 0, right?
Yeah.
So it is in 0 by 0 form, but let's not do that. Like that will involve, maybe you have to do it 2 3 times derivative, right? Because after one derivative it might still be 0 by 0, correct? uh,
Yes.
I will just check it out once. See, first the numerator derivative will be 3x square cos x plus x cube into minus sine x, right? So numerator is tending to 0 and this derivative is cos x into 1 minus cos x plus sine x into derivative of this is cosine x. So this is also tending to 0. So see, one more time now I'll have to differentiate, right?
Yeah.
Because it is still 0 by 0. So it is annoying and you can make mistakes here. So don't do this. Here, instead of that, notice that there is an x cube on top and there is one sine x here, right?
Yeah.
So 1 sine x here. So I know sine x by x limit x tends to 0 will be 1, right?
Yeah.
So I also know that then x cube by sine cube x would have also been 1, right? Sine x by x whole cube.
Yeah.
So if I can get a sine cube x somehow, it will be nice because then this part will be sorted out, right?
Yeah.
So this, what should I do to get a sine cube x? I need a sine square x extra. So I can multiply by 1 plus cos x and 1 plus cos x, right?
Yeah.
So then this part becomes 1 minus cos square x and it will become sine square x, right? So you'll get x cube by x sine x into sine square x, so sine cube x, which is nice. And on top you have cos x into 1 plus cos x, right?
Yeah.
And now limit tends to 0 can be done very easily because this part will become 1, right?
Yeah.
Because sine x by x is 1. And this part there is no problem, it is 1 into 2, right? So 2 is the answer.
Got it.
Okay, so basically the idea is to use your trigonometric limits that you know somehow, like use it somehow and try to get the thing, right? So this is one of them. Then second one, for example, second one you can probably do in second one. See, is a nice question for L'Hopital, right? Because only one derivative will make the denominator 1, right? Correct.
Yeah.
Second one is currently in the 0 by 0 form, right?
Yeah. Once you derive it, it will become one in the bottom.
And after that you can just put the values. So that is obviously a method. However, we can do it without that also. We can just do 2 plus x sine 2 plus x. So sine 2 plus x will be sine 2 cos x plus cos 2 sine x, right?
Yeah.
Minus 2 sine 2 by x. So this becomes 2 sine 2 cos x, 2 sine 2 cos x plus 2 cos 2 sine x plus x sine 2 cos x plus
X cos 2 sine x.
x cos 2 sine x minus 2 sine 2 by x. Uh, okay. 2 sine 2 cos x is here, and well, maybe this was not the best idea. Uh, we could have done something better here. Uh, x. Okay, so one thing different that we could have done here was not expand it like this. Just take common. We can split the first term. We can split the first term and we make it 2 sine 2 plus x, right? 2 sine 2 plus x
Yeah.
plus minus 2 sine 2 plus x sine 2 plus x, right? By x, and take 2 common here, and you have sine 2 plus x minus sine 2, right?
Yeah.
And that will become 2. You can do sine c minus sine d. Sine c minus sine d is 2 sine c minus d by 2. So 2 sine 2 minus, so this becomes x by 2 cos c plus d by 2. So cos 4 plus x by 2. So 2 plus x by 2, right?
Yeah.
And okay, and the next term, so this is one term, this is this much, right?
Yeah.
So divide by x there. So separate out the fractions. So once you separate out the fractions, it becomes 4 sine x by 2 cos 2 plus x by 2 by x plus x cancels here and becomes sine 2 plus x, right? And this is the limit that we want to find, right? So
Yeah.
this part is not a problem, no?
Yeah. That
This
becomes.
that becomes simply sine 2. This part is the part which you have to think about. Here also, this part is not a problem, right?
Yeah.
That is obvious. But this is the thing. So now limit is tending to 0 and we have sine x by x. However, we have to make the argument same. Okay. So here it is x by 2. So I'll put x by 2 and 2 here, right?
Yeah.
And now this portion will become 1, right? So this portion goes away 1 and the answer will be 2 cos 2 plus sine 2, right?
Yeah.
So that will be the answer. You can also get the answer simply by one differentiation. One differentiation here and it will become 1 here, right?
Yeah.
This part will become 0.
Yeah.
So both the methods should give the same answer. Okay. Okay. And third one. Now in the third one, limit of n is tending to infinity, which makes the argument of the sine function tend to 0, right?
Yes.
So argument of the sine function, whenever it is tending to 0, the angle, that means that we should think of the sin x by x and tan x by x forms, right? See, this angle, these two limits are going to be 1 only when the angles are small, right? X tends to 0.
Zero.
Right?
Yeah.
So here a by n, even if the limit is tending to infinity, a by n is tending to what? 0, right?
Zero.
And here b by n plus 1 is also tending to 0, right? So
Yeah.
this is very simple. You just have to make the correct angle in the denominator also, right?
Yeah.
If I have to make a by n in the denominator, I'll have to multiply by a by n in the numerator also, right?
Yeah.
Similarly, tan b by n plus 1, if I have to make there a b by n plus 1 in the denominator, I should multiply by b by n plus 1 here, right? Correct?
Yes.
So what I have done here is I'm utilizing this limit as 1 and this limit as 1, right?
Yeah.
And just to make it happen, I have to multiply and divide by two things, right?
Yeah.
So finally, this will become 1, this will become 1, and you have this expression, right? A
Yeah.
by b n plus 1 by n, right? And this is tending to 1 because divide by n, it is 1 plus 1 by n, right?
Yeah.
This is tending to 1, so answer will be simply a by b here. You understand?
Yeah. Got it.
So basically, again, you're using this, even though the limit is tending to infinity, the angle is tending to 0, right?
Yes.
So that is what we are trying to take advantage of here, right? Then this part, uh, this you can easily notice that this is sine of something and cos of something, right?
Yeah.
So sine cos is a standard formula sine 2x, right?
Yes.
So if I had a 2 sine x cos x, it will be sine 2x. So I'll just write x by 2 into 2, and this becomes x by 2 into 2 sine cos. Okay, I'll not write it again. I'll just write sine of 2 times that, right? Sine of pi by 2x,
Yeah.
right? This is the same thing. Now notice that is if x is tending to infinity, again my angle here is tending to very small thing, right?
Yeah.
So then I just need a denominator of similar angle, right? So I'll multiply, I'll put that there and I'll multiply by pi by 2x here
Yeah.
because I have arbitrarily added this here, right? So I have to adjust that, right?
Yeah.
So
Got it.
this part will become 1 and this part will become xx cancels and it will become pi by 4.
Yeah. By 4.
So this answer will be pi by 4. So basically the trick is to practice questions enough that you are able to do these kinds of manipulations, right?
Got it.
It is just about like getting familiar with it and being able to do this. Then let's do let's do an example using the series ones, using the series expansions that we have learned. The question is limit of x tends to 0, limit of x tends to 0, e power x minus e power minus x minus 2x by uh, x minus sine x, x minus sine x. This is one question. Then second one is limit of x tends to 0, e power tan x minus e power x by tan x minus x, by tan x minus x. Okay, so okay, so let's think of this. Now in these types of questions, whenever there is some function whose series expansion you know, then it is sometimes useful to just write the series, right? So e power x is 1 plus x by 1 factorial plus x square by 2 factorial and so on, right? E power minus x would be replacing x as minus x in this series, right? So it will be 1 minus x by 1 factorial plus x square by 2 factorial minus x cube by 3 factorial and so on,
Yeah.
correct?
Yeah.
So if you subtract the two, what will you get? You will subtract, right? So this will become like this, and 1 will cancel. It becomes 2 times x by 1 factorial. This will cancel, plus 2 times x cube by 3 factorial, and so on, right? So 2 times x5 by 5 factorial, and so on, right? And subtract 2x from that. So subtract 2x from this is 2x only, so this will go away, right?
Yeah. Yeah.
So the numerator is basically 2 by 3 factorial x cube plus 2 by 5 factorial x5 plus 2 by 7 factorial x7 and so on, right?
Yes.
And the denominator now we have to think of. And sin x series we know is x minus x cube by 3 factorial plus x5 by 5 factorial minus x7 by 7 factorial and so on. So sin x minus sin x will be x minus x plus. So we x cube by 3 factorial minus x5 by 5 factorial and so on, right?
Yeah, plus. Yeah.
This type of series, right? So
Yeah.
denominator is this x cube by 3 factorial minus x5 by 5 factorial plus x7 by 7 factorial and so on. And I have to take limit of x tends to 0, right?
Yes.
So to take the limit, let's divide by x cube because right now it is 0 by 0, right?
Yeah.
So divide by this power so that this will go away and you will get these terms will be x square and so on, right?
Yeah.
All of those will disappear
Yes.
and what will be left is 2 by 3 factorial on top and 1 by 3 factorial in the denominator. So answer will be 2.
Got it.
Okay, so the reason I divided by x cube is to cancel off that power and get the limit, right?
Okay.
Are you understanding?
Yeah.
So here again series expansion, knowing the series expansion is useful here. So if you look at the next one, for example, next one is 1 second. Next one is this one, e power tan x minus e power x by tan x minus x. Limit x tends to 0, e power tan x minus e power x by tan x minus x.
Right.
Okay. So this, you know that this limit is equal to 1,
Yes.
right? So
Yeah.
now uh, for a moment let's think of this. If I take e power x common here, what comes on top? E power tan x minus x minus 1, right? By tan x minus x, right?
Yes.
So can you see that if I take y as tan x minus x,
It will be e to the power y minus 1 by y.
e to power y minus 1 by y, and y is tending to 0, just like x is tending to 0, right?
That would be 1.
So this limit will become 1 and e power x is 1 only. Answer is 1. So standard form, like remembering the standard form is useful because if you know that x tends to 0, this limit is 1, I will just take common e power x and I'll make the denominator and I'll fit that pattern, right?
Got it.
Okay. Uh, Now what we have is basically one thing is left, which is the exponential type of series. I will not start that now. We'll do it in the next class. Exponential limits. When it is something like this, 1 plus x to the power 1 by x, where limit x tends to 0, something like this. It can be also 1 plus fx to the power gx, where limit of x tends to 0 and this part tends to 0 and this part tends to infinity as x tends to 0. So these types of exponential limits we will see in the next class. What you should do is practice your exercises from your limits from your book, right? You will have many questions there.
Yeah.
Uh, do as many as you can. Whatever problems you have, we can discuss in the next class also.
All right.
Okay. Tomorrow evening we'll do chemistry. Read up a little bit on the chapter 2 and chapter 4 and all that we were discussing. So
Yeah.
we will continue from there. Organic. Okay.
Okay.
Okay. That's all for now.
Thank you.
Mm, bye.